Okay. Before I forget, we're going to be talking about string copy today. That was the issue we were having um, last class, which wouldn't have been an issue historically, but I'll explain that in a second. I did just, because we're going to be, I've kind of indicated we're going to be writing a web server as we kind of move forward here. One thing that'll be helpful for you is there's a program called telnet. How many of you have used telnet before? Okay, so telnet allows you to remote into a server over the internet somewhere at the command line. So as a quick example here, if I say telnet to www.google.com port 80, which is their web server, and I press enter, I'm effectively pretending to be a web browser. All right, so I'm sitting there at the, I'm connected into their HTTP server, and I'm going to say I want to get index.html, which historically was the name of the main homepage, but I don't think it's the name of their main homepage, so it's probably going to give me like, couldn't find this page or whatever, so I'll do that. I'm asking it over the HTTP protocol to retrieve for me the file named index.html. Since its MIME type is HTML, it's not going to do any pre-processing. It should just spit out the result to me. It's going to give me some HTML-y looking stuff here. And up at the top here, you probably see that it says error 404 not found. So that wasn't a page that it knew about, but it still spit out some stuff. We're going to be experimenting with some of this probably later this week, but just in case, it doesn't actually come stock on your install on here. So the command you want to use to install it is this command right here. So there's a package manager on Linux, depending on which distribution of Linux you have. It might be Yum, it might be apt-get. There's one for SUSE Linux called, it starts with a Y, I forgot the name of it. But whatever. Whatever the package manager is for your Linux distribution, if you're using Cloud9, it's Yum, which came from, it was one of the popular ones that Red Hat made popular. So you'll say sudo, which says I want to do this as the super user, then space Yum, name of the program, and then you want to install a program called telnet. And if you do that, it's going to go through something like that. It's going to see that I already have the latest version installed, but earlier today I installed it. So that's the command you want to put in to install it. There's the command again. You want to just write it down. Or if you want to do it right now, it takes 30 seconds or something to install. Once it pops up, it'll ask you, do you want to install it? And there's like, press Y, lowercase y, and press enter, and that'll agree to it. And then it downloads and installs everything.
I got command not found.
You got command not found on Yum?
Oh, got it.
Now this is actually kind of an interesting, maybe a little bit of a backstory. I know I asked before how many of you have done anything with Linux before. Only a couple of you. Roger, how many of you have messed around with Linux on a computer before? Okay. Now, generally, a modern person, when you, it's SUSE, the program's called YAST, Y-A-S-T. That's SUSE's package manager. But in any case, if you've used Linux in probably the last decade or something like that, package managers have existed. So if you're ever going to install something, 9 out of 10 times you're going to be able to do something like a Yum install, whatever. And what it does is it looks at any dependencies. So you might have one program that it depends on 11 other programs. Well, it'll install all of those for you without any trouble. So you don't have to do any extra work. And if you had used Unix historically, that is a huge help because you used to have to compile all your programs. So we're used to when we use Windows or something, you double click on setup and it sets everything up for you. And every now and then it'll say, this program requires the .NET C# redistributable whatever, and it'll download that for you and install it. But generally, your computer already has everything it needs. Well, historically, if you were going to install something like telnet, you would download off the web somewhere the telnet, what's called tarball. So, somewhere there would be a file called, something like telnet.tar.gz. They usually called those guys tarballs. Yeah. Well, no, this is a tape archive, so it's archived first, then compressed, then gzipped. Sometimes you would see TGZ, which was just a little bit a different program that kind of tarred it and zipped it at the same time. But, the historic slang for this was tarball. I guess balled it up was zipped it up, and I don't know if there's a backstory to the name. It's entirely possible the backstory is an inappropriate one. Several things with Linux are, but I don't know what it is. But in any case, what you would do is you would download a file like this. You would have to unzip it, untar it. Then you would have to go in and you would do something like once you're in the directory with it, you would do like a /configure. And that was like a script that would run that would ask you all these questions of what you wanted to support, this feature or this feature, things you could turn on and off as you're installing it. Then after that, you would do something called a make. And a make file it compiled a whole bunch of different pieces of source code. So rather than you having to type in GCC this file, then GCC that file, and GCC some other file, you would type make, and it would go through and it would compile the correct source code files in the correct order. So this is something they had to set up as part of the installer. And then after you did that, so that might be something it took for a relatively small program, maybe it took a couple of minutes. For, there was a version of Linux called Gentoo Linux that you actually compiled the entire operating system. And did the bootstrap and everything for the operating system, and then you could be compiling for hours and days. So you would just leave your machine overnight and just let it compile and compile, only to come in the next day and find out that something failed and you were missing some thing. But in any case, make would go through and do a bunch of compiling stuff, and if anywhere in there it failed, it would tell you, such and such not found, because it was looking for some, like a pound include. Libraries like we've been bringing in header files, it was looking for some header file that it couldn't find because you didn't have the program that provided that header file already installed in your computer. So you would look at the error, then you would go and find the tarball for that program, you would download it, you configure, make, install, assuming you got through the make on that one, because that one might have other ones that it was relying on. So it was this wild goose chase. You went all over the place until you finally could get the thing to build. And then you would do a make install. So your last thing would be make install, which would effectively copy the executables into probably user bin or user local bin, kind of one of the common folders where your executables would live. This is kind of equivalent in Windows to the program files folder, something along those lines. You can run a file out of any folder if it's executable, but that's just kind of the common bucket where they might get put. So in any case, installing a program on Linux could have been, or on Unix, this was Unix before it was Linux for doing this kind of stuff. It was a major task. You really felt like you were installing your stuff. And you can imagine that as programs get more and more complex, most of the time for us, we're doing these little assignments and things like that. Our programs are just one, maybe two files, right? Some of the Android stuff, you maybe had 5 or 6 files, and half of them were XML files or something like that. But generally speaking, what we're doing in here as examples or in any of your classes are small. All right, and maybe for your senior seminar project, you get into something that's larger that has multiple source code files and things like that. But we're also using modern tools where you just hit a nice little play button and it does the magic of making all the things talk to each other. So we should have an appreciation for kind of where these things came from. Well, even though this still feels primitive to us, going and typing something like that to install a program, that is like so far in the future compared to how things used to be done on Linux or Unix, that it's a super big help. So Yum is a package manager that it installs things called RPMs, which Red Hat, RPM was the original Red Hat package manager. So that was one of the early cool kids for package manager things. So it would have your files, instead of as tarballs, it would have them as RPMs, which were like more convenient to install. And then to take it up another level, a program like Yum says, I'm going to check a particular RPM and say, what other RPMs does this guy rely upon? And I'll go and install them first. Then I'll install this guy and I'll do all the magic for you. That makes sense? Makes your life a lot easier. So from your perspective, do a sudo yum install telnet. I don't even remember if it downloaded anything else. Actually, I probably can scroll up here and find it, because I did it like 20 minutes ago. Your terminal is in collaborative mode. Oh, whatever. Is that bad? Yeah, it doesn't seem like it likes it. I tried to... It doesn't like me trying to scroll up.
What did you want to know? I just...
Oh, like does it install anything else? Does it say requires such and such package downloading and then install, then it says okay after it or anything? Or did it just download the telnet? Well, I'm just saying I did it not that long ago. I was going to try to scroll up to see what I had done, but that didn't seem to be something that...
Yeah, it's only telnet.
Okay.
It did like a resolving dependencies thing, but...
That's that resolving dependencies is it trying to figure out what else it might need. So, and it only took a couple seconds, right? It was quick.
Yeah.
All right. So, in any case, do that so you have telnet available. We're not going to use it today, but that is something we will be. Actually, I already showed you it once today, so we won't be using it officially today, but I kind of already showed it to you. We will be finishing our stuff from last class. What I will do is when I go to grade the assignment from last class, I'll just give you automatic full credit for the change in place. You could have accomplished it, but as Muath pointed out last time, technically the version that I wrote uses new memory. But we then in me trying to do that, we ran into an issue that I want to spend some time talking about today. That actually is an issue that... It's a modern issue that we've seen before, if you've taken any of the Java classes with me, that was never an issue before in C, because in the early days of C, strings weren't a thing. Everything was just a character array. And then strings became a thing as people started using the language at a much more powerful level, and that's why we have string.h, which is another header file, which we'll talk about a little bit today. But for starters, let me just... remind or try to trick some of you. Just going to give me, okay, this is fine. So I'm just going to open a quick Java program. So switch your brains to Java mode for a few minutes, okay? Because this actually is related to what we're going to be talking about today. Now, one thing I'll just point it out, you're already seeing it in this class so far. One thing I'm really trying to do, and you hopefully you're seeing it in your 300 and 400 level classes, is we try to bounce between different technologies to really emphasize that idea that, for my world, computer programming, the language is insignificant, right? We're kind of doing the same crap just with different languages, and they each have their own little idiosyncrasies. But now that we're getting, within spitting distance of graduating, we're going to be dumped out into the real world where we're going to be getting jobs in some place, and you might not be using a language that you had in school. But hopefully we're starting to see that it's kind of the same crap. You'll spend a couple of weeks figuring out all the stuff that doesn't work because it has these little, twists and turns that are just a little bit different than some of your assumptions that you're coming in with based on the languages you have worked with. And then all of a sudden you'll realize that 90% of them is something you can apply to whatever language you had historically. All right. So what I'm going to do here is I'm going to go ahead and create a string s, set this guy equal to hello, string s2, is equal to hello. String S3 is equal to new string hello. And then we're going to go ahead and I'll put it in a Boolean. I'll say Boolean answer is equal to S equal S2. All right, so I'm storing inside of answer the result of saying S is equivalent to S2. What should that give me, true or false? True. So go ahead and run this. So there's my true. All right, then we'll say S3 equal S2. What should that give me? Who thinks true? It's not embarrassing. Most of you, the people that immediately shouted false out, have remembered this lesson from before. Several of you, I'm sure, think, well, why shouldn't that still be true, right? So the first time I would show something like this, you would say, most of the class would guess that they are the same. They both hold hello. I go and run this dude, and it gives you a false. Okay? If we go up here, we ask ourselves, what is that guy? That's the primitive equivalence operator, right? So what we're actually doing here is we're not seeing if hello is equal to hello. We're seeing if the memory address stored in S3 is the same as the memory address stored in S2. All right? And this ultimately comes down to something that Emma brought up at the end of class last time called literal space. Well, I think she pointed out it had to do with literals, but we have in our modern programming languages, we have something called literal space. So if we're talking about Java, and I say string S is equal to hello, that's going to go and it's going to check literal space, see that there isn't currently a string in there called hello. It will then create a string in there called hello. And just for the sake of argument here, let's just say that this guy happens to live at memory address 100. All right, so we would say that S points at hello. Okay, well, that's actually not true. We would say S points at memory address 100, which happens to contain the pointer to the beginning of the string hello, which is somewhere else in memory probably. Okay, well then we create a string S2 and set that equal to hello. Again, the value we're setting S2 equal to is a string literal called hello. So we're going to check our literal space first and say, do we already have a string in literal space called hello, which contains hello? We do. And since we do, what it'll do here is it'll create S2 and make S2 point at the same place S points at, to that single literal hello in memory. That's why S and S2 are equivalent to each other. S equal S2 will be true because they are both 100. Does that make sense? They hold the same memory location. Now, when I say string S3 is equal to new string hello, and this is actually one of the things that makes Java kind of a difficult first language to teach, is that strings are the only objects in Java that are treated differently. We might look at this and we might say, oh, well, because strings are so important to the Java language, the good people at Sun Microsystems, now Oracle, gave us kind of a shorthand syntax for working with strings. a lot of times I'll refer to this type of thing, you've heard me say this before probably, is syntactic sugar. You've heard me say that before, right? Okay, so I call that syntactic sugar, just shorthand stuff to make the syntax a little friendlier. Now, the issue with this, though, is we get lulled into thinking that these two lines are functionally identical when they're actually functionally similar. The difference being is whenever we see the new keyword, we should think that we are personally requesting new memory. That guy's going on a mission for us to go find new memory somewhere in the computer. The second we say new here, we're saying we're not relying on literal space because we are not asking the value to be the literal hello. Instead, we're asking the value to be the memory address that results from calling the constructor for string and constructing a brand new string containing the literal hello. So what this will end up doing is it will create a new place in memory. Just so happens it's a very convenient operating system. This is memory address 200. It's going to put hello there. Why aren't addresses ever that friendly looking? It's almost like they just randomize like a whole bunch of hexadecimal hextets.
Well, isn't the entry point always like 0 and something?
Well, that says it's hexadecimal.
Yeah, but it ends with 100, right? The entry point.
It'll end with whatever the offset is, wherever for that particular operating system, it reserves so much space that's secure for the operating system itself. That's the modern microkernel way of doing things. But the bottom line is you never get nice addresses like 100 and 200. Just yeah. It's garbage. That would actually be a very interesting random number generator. Is just keep calling new until you finally get a memory address that's like less than, I don't know, 1,000 or something. Well, you never get that. You'd have to figure out what's the end of legitimate system space for the memory. Whatever operating system you're using, they're going to say, look, this is ours. And you can't touch this. They protect it. That way you keep programs from overwriting part of the operating system, which used to not be a thing. You know, old kernels used to just say, look, we'll find a place in memory just like any other program. And that's where buffer overflow stuff really became dangerous. All right, so we'll have this. We'll go ahead and give ourselves the S3. And S3 happens to point at this place in memory, which is why S2 equal S3 gives us a false. They point to different places in memory. That makes sense? This is how Java works, and this is also how our modern C is working when it comes to string literals, which is smart, but it's an upgraded mentality for not being wasteful with space, right? If you have a string literal hello that you've created in a program, it would be a waste of space to create hello 30 times. Right? If you create 30 variables for no good reason and set them all equal to the string literal hello, it would be wasteful to create hello 30 different times in memory. You'd be better off creating it once in memory and having all 30 of those variables point to the same single place in memory. That makes sense? As opposed to, so that's what became interesting here, where we ran into this last time. Is forget about this string copy here for a second. I'm going to come back and talk about that. So we would create a char pointer s, which we're mentally thinking of as strings. But if you think back to the early days of C, it was a string, but C didn't have inbuilt the ability. It just represented them as char pointers, char arrays. So we say s is equal to hello. What we just did is we changed. In fact, actually, I want to see if I can prove that here real quick. Here, we'll do a multi-line comment just for the sake of remembering that's a multi-line comment. I'm going to go ahead and say printf %p s, and then I'm going to steal that line. And we're going to do it again. They're different addresses. So what we did here is we said, oh, this is us calling the new keyword, right? That's the C scary version of calling the new keyword. Allocate some memory. How much memory? 50 times size of char, blah, 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 blah. Then we printed out that pointer. So here's the pointer for that memory address. Then I immediately overwrote that memory address with a brand new pointer. The pointer to hello in literal space, which presumably this was the first time we created hello in literal space. So if I do this, if I say char pointer s2 is equal to hello, and then I go ahead and I print out s2 here. See, those guys both point to the identical place in memory. So the string literal hello exists once in memory with two different dudes pointing at it. S had a nice place in memory big enough to hold 50 chars for just a moment. Actually, it's still there because in C, at least original C, we're very used to in Java having automatic garbage collection, right? In C, you don't have that. So what we just did here is we created a memory leak. Okay, so I created a brand new place for memory. So I went down the street and we just built this 50-character mansion. Okay, built a 50-character mansion. Then immediately said, we're going to forget about this place. And now we went over to probably the hello literal is like a tiny home. Right? So we went over to the tiny home over there, abandoning the mansion. Nothing points at that mansion right now, right? The only thing that used to point at it was S. So that guy, so this memory address had a pointer count of 1. As soon as I set S to be equal to the address associated with the hello literal, the pointer count to this memory location became a 0. In the Java world, that would then put it in line for automatic garbage collection. In our world, we're just leaving a mess behind. We just abandoned it. Like, what was that? I just saw it the other day, the Brazilian Olympics style. They like abandoned all the venues. They built all these, and so you get these multi-million dollar, like I saw the aquatic center. The thing's like in complete disrepair. So we just did that. Yeah, you just said it's sad. But you know what? Modern computers, we got 2 gigs of RAM or whatever. Sure, we'll reboot our computer before this is a problem. or somebody else will reclaim this memory. Realistically speaking, modern operating systems are probably going to have mechanisms in place to reclaim this memory. Notice that it has 0 pointer count, but it's not a guarantee from the language itself. Java comes with automatic garbage collection. C natively does not. It would then be relying on the operating system, the memory manager of the operating system, to do any sort of optimization to say, hey, this is just wasted. You just abandon this plot of land, and it would just then mark it off as not being handed out to somebody, and somebody else could then come and build over it. All right, so does that make sense? So what we were doing last time is we effectively broke our, this move right here, really the 2 lines. We're saying, I'm going to go create some brand new memory, and then I'm going to immediately walk away from it by making S point to something else. Okay? So we have a library called string.h. Well, here, I'll go ahead and here's string.h. Let's make it. Man, I hate that.
That's so pointless.
It says I'm in collaborative mode. Is that the problem? Yeah, that's something else. That's a browser thing. Actually, here, until we figure that out, I'm going to just do it out here. So there's no man page for string.h. All right, so just dumb. All right. All right, so pretend like we looked at the man page. So here, so string.h has a bunch of functions in it. We happen to only be looking at the function for string copy. Okay, there are other functions in there, but the Mac being the Mac decided it's not going to have a man page for that. We saw that Linux had a man page for that. Garbage. But in any case, we have this thing called string copy, this guy right here, that we pass in a char pointer to our destination. And then we also pass in a char pointer to our source. So what we would say is we would pass in S to this guy, and then hello to this guy, and that would say copy the contents of hello into the memory space that we just requested from malloc, not breaking our pointer. So let me show that to you. Okay, so everybody understands that we broke our pointer right there? So let me go ahead and dump this guy and dump this guy, and we saw that S is two different values here, right? Go ahead and run that again real quick. Do I not have a terminal anymore? Lost it? Nope, down here. All right, so I'll just exit out of this guy. Go ahead and run this again. So, different memory addresses, right? Broke our pointer. Now what we're going to do is instead of overwriting S with hello like that, we're going to say strcpy, string copy, and then it wants us to send it in the destination pointer. Where do I want to write my string to? I'm going to write my string to there. And then what am I writing? I'm writing hello. All right. Now this guy will return a pointer. And here, we'll even want to do this. We'll say char pointer answer is equal to that. And then I'll go ahead and print out answer here. All right, so I get memory, prove I have the original memory address. Then I use string copy to go to the original memory location and fill it with hello, not overwriting the location. I fill it with hello. Then I can print out that memory address, which should match this memory address because I haven't overwritten the memory address. Then we'll print out answer, which I believe should match this memory address as well, because I think this string copy shoots out a pointer to the destination. Oh, is that saved? Yep. So, original memory. They're the same pointer after string copy, still original memory. And then the result of answer, which seems redundant to me. I don't know why you would need that extra pointer firing out of there unless you were, yeah, I guess that would probably be for like an inline function where you needed the answer there and couldn't get to a variable that you were setting later on or something. But in any case, it's the same memory location. That makes sense? Okay, so now we're working with identical memory and can reverse it. So now if we want to be, I guess, smart kids, I suppose, since we now have this cool trick for reverse, for reverse string in place, I can call reverse string, like I'm doing here, to get me my answer, right? Then Okay, so this guy should not need a pointer in this case. This will make more sense now. So I'm going to just take in a string, as well as the length of that string. I'm going to call reverse string, passing in that string and its length. This is going to give me a brand new string, which is the reverse of the original, right? Then I'm going to go ahead and I'm going to call string copy into S answer. So I'll overwrite S with answer. So let's get us to here. So we'll go ahead and get our string copy. We'll fill up S with hello, not change S's pointer, just fill it up with hello. Then we're going to go ahead and call, reverse string in place, passing it S, and we can pass it either the real length or whatever, so we'll pass it the length we had just for testing. That's fine. So reverse string in place, S and 5. So beforehand, we'll do a printf %s \n. We'll print out S. So that should be hello. Then we'll call reverse string in place. Notice we're not returning any values here. Reverse string in place is going to first call reverse string internally, then copy the result of reverse string over the original memory location. We'll printf we'll print out S again, the actual value that lives there. Oh, I need to go down and fix my, this guy now just takes a single pointer. So there's my hello and my reverse of hello. And then if we want to really, make sure that we didn't break memory, same memory locations. So there's muout's in place. Make sense? And now we could have also just done the reverse, thing again, actually overwriting the memory locations, knowing now that we were working with the real memory location. So we didn't have to use our original reverse string if we didn't want to. We could have brought this logic into our reverse string in place and just change the location of that, since we are now working with the same place in memory. Does that make sense? Yeah, because this is the logic to reverse a string. Just so happens we were reversing it in the original location. So, we would probably have created a copy, made the reverse there, and then if we didn't want to use string copy, we could have gone and overwritten one character at a time in that original memory location, because we were manipulating the original memory location. All right, so questions about the string literal stuff and things like that. What, for strings? Yeah, that's fine. Yeah, you're going to want to. And I'll introduce new things, but I'll just blanketly say if there's something related to strings that you want to use the library for, go ahead, because it'll make your life easier. It doesn't fix a real problem for us. Yeah, we're going to still be working with enough memory, enough stuff in here where we'll be directly working with memory through integer arrays and stuff like that, that you'll get plenty of memory practice. Concatenate? Well, no, there is a concat function for strings.
Or in the library.
In the library.
Yeah, but I have to write my own.
Well, you could write your own concat function. Yeah, that's fun. As long as you have enough memory space. You got two strings, you want to put them together, as long as you have a big enough landing zone. It's not a big deal. You just find out how long this one is. Make sure you put the other one after that in memory. That way you don't overwrite.
And you have to also end it with the null pointer.
You mean the \0 thing? That's not a null pointer.
Isn't it?
No, that's the termination character. Yeah, termination character. And null pointer would be like char pointer equal null. Although in C, is it nil or is it null? No, I would think it would be NIL, just one L. But we'll bump into it at some point. It'll be one of those two. It won't be NILL. I'll promise you that one. It's going to be NULL or NIL. Or if you're in Swift, isn't Swift none? I think Swift is NONE. Who even knows what Visual Basic is? Maybe Visual Basic might be like nothing. It might literally, the word might, Visual Basic uses some weird things that actually make a lot of sense. Like in Visual Basic, we're used to like the keyword this in object-oriented languages. In Visual Basic, it's me, which actually makes sense, right? I've said, it's how an object refers to itself inside of itself. Well, when we're walking around and we're talking about ourselves, we don't say this, we say me, right? So kind of makes some sense.
It is nothing.
It's what?
It is nothing.
It's nothing. Yeah, that makes sense. Let's see, what was that? Oh, so how is what's the equivalent of this in C? Sort of kind of a trick question. There is none. Why? I thought you were going to be so smart.
Oh,
You...
no, I just got
No.
That's the easy part.
Because you just always play with the ad,
You always have the base address.
All right, here, I'll ask the easier version of the question. What's the syntax for objects in C? It's not an object. Objects have functions in it. What's the syntax? It doesn't have objects. It's a procedural language. No objects in C. Therefore, no equivalent to the this keyword in C because it's not an object-oriented language. Disappointed me, Muha. Apology not accepted.
It's just like, why would you show us Java first when everything you've shown us after it has been works?
Well, but keep in mind, so this kind of goes back to when I do show Java, I'm constantly spending time looking at what's under the hood in Java, even like well, you'll never have to do this in Java, but here's how things actually work, because Java just hides so much stuff from us, which is nice. It's convenient as modern programmers, but then when you get thrown into a situation where you actually need to know how things work under the hood, you don't have it. It's not knowledge that you have. That's kind of the real life problem with some of those like programming boot camp type things. It's not that they can't be great. If you're going to go out and be a Ruby on Rails developer and that's what you're going to do the rest of your life, you don't need to know how this crap works under the hood. Just be really good at Ruby. Just move on with life. Okay? But if you need to be more of a cross-training type athlete or whatever, knowing how this stuff actually works is going to benefit you as you jump from language to language to language, because then you're going to ask that question, okay, how does this concept work in this language? And then you'll figure out the weirdness in that language for that concept, and now it all makes sense. Okay. The book. We're going to start looking at file I/O. Does the book have a section on files? Okay, I know we're bouncing around a little bit, but this will be important for us. It looks like, let me just look at all of chapter 9. Yeah, I mean, it's a pretty short thing. So for next class, go through chapter 9 and do all of the interactive exercises. I haven't looked through it yet, so if they do reference something that's older that we hadn't covered yet, that's like weird, just skip it. I doubt they will, because I think it's really just going to be normal input, normal output, just using file pointers instead. So go through chapter 9, do the interactive exercises. Next class, we will, I might do a quiz on file pointer stuff. It's not real difficult because in Linux, everything's a pointer. So, and everything's a file. So whether you're writing to the screen or writing to a file, it's actually kind of the same thing. All right. I'll see everybody on Wednesday.